rainfall, and really I'm going to talk about the biggest of the big storms, so the extreme storms, the ones that cause the most damage and produce the most rainfall. And we'll talk about how we analyze these storms and how we use them to come up with information that various people and governments and infrastructure use to design structures and to keep people safe and to protect us from floods and so on. And one of the main points that's very important to understand, and kind of a theme throughout the entire talk, is the importance of your CoCoRaHS data, and that we get it in a timely and accurate fashion. You'll be amazed at how much we actually use the CoCoRaHS data in all these analyses, and these are studies that end up dealing with millions and millions of dollars worth of infrastructure. So your one rainfall report, you may think it's insignificant, but trust me, it's not. It's very important, and to have that accurate data is very, very useful for us in many ways. So we'll go through all those things today and hopefully have some fun talking about some big storms across the country. So a little bit of a history behind storm analysis in the U.S. The National Weather Service and the U.S. Army Corps of Engineers did a systematic analysis and cataloging of extreme storms across the U.S. through about the early 1970s. They started in the mid-1930s, and then they stopped. Well, of course, it didn't stop raining. We continued to have big storms go on, so something had to happen. Now, when they were developing all these catalogs of extreme storms, they were using the data for a lot of different purposes. Of course, lots of research involved in things like atmospheric rivers or the Pineapple Express and how those storms affect flooding and rainfall, and how those rainfall disasters can cause so many problems like these landslides that happened in January of 2005 in Southern California. Also things like precipitation frequency or the rarity of a given rainfall event. Well, that rainfall data that the Weather Service and Corps of Engineers is collecting was used in those types of analysis, and that's very important for infrastructure development and flood design, especially at a local level. And then also things like climatology. The PRISM group out at Oregon State University has developed a lot of great information on rainfall climatology across the United States and parts of the world as well, and they have to have accurate data to do that. Other things, of course, like dams. The top dam there, the Hoover Dam, that's a pretty damn good dam. It's doing great for a number of years, but you have to know how big to build that dam to hold that reservoir behind it. The Teton Dam in Idaho wasn't such a success. It had a sunny day failure back in the 1970s. And again, if you don't understand how big the floods are that could be caused by rainfall at a given location, that might happen to your dam. Other things that are used this rainfall information for are things like nuclear power generation and hydropower generation. So there's lots of things that are dependent on accurate and timely rainfall data and analyze storms. But as I mentioned, the Weather Service stopped doing these storm analysis, and so we had to have some way to continue that going forward. Well, what did the storm analysis look like that the Weather Service performed through the 1970s? Here's an example of one of the images that they put together when they're doing a storm analysis. On the top left there, you'll see that they put together what's called a storm isohydal pattern. That's kind of a general pattern of the overall rainfall footprint at a given location. And you can see that this storm occurred in the Ohio River Valley mainly. This was back in March of 1913 and actually resulted in one of the largest floods, very damaging flood along the Ohio River Valley from Ohio down to where it hit the Mississippi River. On the top left, you have your general storm information, things like the date of the storm, the assignment number that they gave to it, the study area that it was prepared for, and the dates of the analysis. And then in the middle there, you have the number of stations that were used and the station types. So some of them were hourly precipitation stations. Some of them were daily, which would be like your CoCoRaHS reports, although, of course, CoCoRaHS wasn't around in 1913, although I'm sure no one was thinking about it at that time. And then on the very bottom there, we have our depth area duration table. Now, this is a very important piece of information. It gives us a three-dimensional look at a given rainfall event. So instead of just having a really high point rainfall event, say in your backyard, you might have recorded 11 inches of rain in a day. That's great. That's very important to know. But what does that mean for a given area of, say, a total city or a county or a state? How much rainfall fell over, say, 1,000 square miles in 3 days? It probably wasn't 11 inches. It may have been something different. And that's very important for people to analyze because that data is used to analyze flood hydrology, especially volume and peak, and that's what you usually design against. The other sheet that's included in all these storm analysis, Weather Service, and the Corps of Engineers were the detailed isohydal storm patterns. And you can see how they have increments of rainfall from 2 inches to 3 inches to 5 to 8 to 10 and so on, which show you where the heavy rainfall sensors fell. And then on the bottom of the sheet, they have what are called mass curves. And these relate how much rainfall fell in a given time increment. So you can see that the rainfall may have been light for a day or two, and then you had a burst of heavy rain all of a sudden, and then the rain was light again for a while. And that's very important for an engineer or a hydrologist to understand how that rainfall pattern is occurring, so that when they're modeling the resulting flood, they know if they have to deal with a big peak of flood coming through or if there's a general large volume over a longer time period. So those were all very important information pieces that were done in all of these storm analysis in a standard way, and that were used by various groups to understand the rainfall events. But again, they stopped doing these in the 70s, and of course, as I mentioned, the rainfall didn't stop happening. As we know, we've had lots of big rainfall events in the last 20, 30 years, and that data was still needed, and is used all the time up to this day to continue to do these flood analysis and infrastructure development and design and safety analyses and so on. And so somebody had to step in and come up with a consistent way to perform these analyses. And as usual, for things that advance the science or advance technology, these are developed out of necessity. There was a little bit of storm analyses done between the 70s and the early 2000s by groups like the USGS, the Bureau of Reclamation, and even Nolan's group there at the Colorado Climate Center did a great storm study for the state of Colorado. It was published in 1997 on extreme rainfall storms in the state. The problem, though, is that most of those previous analyses were not done in a consistent manner, and they were done to fit a specific need of a study or a client, and so weren't really usable by a wide community. Well, in the early 2000s, when Applied Weather Associates began to do site-specific probable maximum precipitation studies, which we'll talk about in a little bit, we had to have some way to analyze the storms that had occurred since the 1970s up through the 2000s. And so we had to develop some kind of process to do that. And of course, we wanted to be able to use all those previous 600+ storm analyses that were done by the Weather Service and the Corps of Engineers, and be able to marry those up with the storms we were doing for these new studies. And so we built a program that followed the general pattern and architecture of what the National Weather Service and Corps of Engineers had developed. This is part of NOAA, National Weather Service Technical Paper 1 back in 1946, which kind of gave the details of how to do a depth area duration analysis. Of course, being that it's a new computer age, we're able to use a lot of updated technology and processes to automate that quite a bit, and we'll talk about that in a minute. But first, let's take a look at some of the storms that we've analyzed over the last 10 years or so using our system. It's called the Storm Precipitation Analysis System, or SPAS. And this is a map of the storm locations that we've looked at east of the Continental Divide. And you'll notice they extend all the way up from the infamous Gibson Dam storm of June 1964 up in north-central Montana, all the way up to northern Maine, and down in Georgia and southern Louisiana, you have a Hurricane Gustav landfall in September of 2008, Hurricane Katrina, of course, in August of 2005. In the Midwest, you have a number of big thunderstorm events and mesoscale convective complexes which produce a lot of rainfall. 24-hour state records in Missouri from Edgerton, 1965, and 24-hour state records in Illinois from Aurora College, 1996. So all the big ones. I mean, that's the cool part of what we get to do. We get to analyze the biggest of the biggest and see what those rainfall events look like. Along the West Coast, also lots of storms we've analyzed for several studies out there, extending from southern British Columbia down to southern California, including some of the big ones in California, like January 1943, December 1955, the great Christmas blowdown storm of 1964 in Washington and Oregon, and so on. So lots of storms there. And then Arizona kind of gets to be a special little state of its own, because a study we're doing for the whole state there, where the past work that was done by the Weather Service and Corps of Engineers in Arizona, they didn't analyze any storms the way that anybody does them now, and so there was no information available on those storms for Arizona to analyze. And so as part of that study, we had to analyze 47 new storms just for the state of Arizona and see all those storm locations there. So that's pretty intensive, but a pretty cool process, because we've had a really good chance to get familiar with the storm environments that create heavy rainfall in Arizona, ranging from the Southwest Monsoon season to remnant tropical systems coming up the Gulf of California and then making landfall and producing a lot of rain in California, like the remnants of Norma in 1970. And then also Arizona gets hit by a lot of winter storms, especially in the January-February time frame. So you have 3 distinct storm types that occur across the state in a given year. Now again, the way that we analyze these storms, pretty cool. It's called the Storm Precipitation Analysis System, as I mentioned, or SPAS. Now, we're not real good at acronyms, so you might want to prefer to call that SPAS, but we like to call it SPAS. And this was developed jointly with our partner called NEXRAD Incorporated, and Ty Parzybach does a great job up there in Windsor, Colorado, and helps out a lot with this. So to date, we've done over 240 storm analyses, and we've also been able to reanalyze some of those older Corps of Engineers and Weather Service storm events. And what happens is, with SPAS, we're able to do a gridded precipitation analysis at about 1/3 of the square mile resolution, so pretty small resolution. And usually at a temporal resolution of about an hour for any given storm event. But if we have NEXRAD weather radar, we're able to move down as low as 5 minutes. So we're able to look at the rainfall across a given domain in a really high resolution, both spatially and temporally. And this gives us a really good sense of how the rainfall fell in any given area. Now, this process is automated as much as possible. I mean, of course, we want to take advantage of computer power and technology wherever we can to speed up the process and to help in the QCing and QAing and just really help wherever we can to make the process happen faster, especially when you realize that the Corps of Engineers, when they were doing these storm analysis, it usually took them about a year to a year and a half just to do one storm. Well, when we use SPAS, we can get this done in a couple of weeks time frame, so that's a really big advancement. Of course, the big problem in the past was you had a set of rain gauges, rainfall reports over a given area, but you had no idea how much rain fell in between those rain gauges. How was the rainfall spatially interpolated? Well, back in the day, you had to pretty much use your best judgment and simple mathematic weighting formulas and see some polygons. Well, now we've been able to advance that quite a bit, where we can include things like climatological base maps from that PRISM technology we talked about, or just average monthly precipitation values. That gives us a picture of what an average rainfall event would look like spatially, and that helps us to interpolate between those rain gauges and really fill in those values. And the other very valuable piece of information that's become available since about the mid-1990s is a NEXRAD weather radar, which does an excellent job of telling us how rainfall is falling spatially at any given time. Unfortunately, it doesn't do such a good job with telling us how much rainfall is falling or the magnitude of rainfall. So we have to adjust that to fit the rain gauges. And so we have a nice process within SPAS that kind of takes the best of both worlds, the NEXRAD weather radar spatial information and the rain gauge magnitude information, and marries that up to give us a great picture of a rainfall event. And it's important to remember that rain gauge data is considered ground truth, and that's what everything else is built off of. And that's, again, why it's so important that we have accurate CoCoRaHS data to use at any given time. So let's take a quick look at NEXRAD weather radar and how we use it to come up with the spatial distribution of a given rainfall event, and also adjust it to come up with magnitude. Because think about it, what's the chances that your 4-inch CoCoRaHS gauge or an 8-inch tipping bucket gauge or whatever you may have actually received the highest amount of rainfall over, say, 1,000 square mile area during a given rainfall event? It's very, very unlikely. And most likely the heaviest rainfall fell somewhere in between those rain gauge reports. And so we have to figure out a way to analyze that and quantify that. And this NEXRAD weather radar really helps do that. So what happens is you get this raw NEXRAD weather radar across the country going on all the time, and in southern Canada. And that data comes in basically unquality controlled directly into a vendor that we use called Weather Decision Technology, based out of Norman, Oklahoma, there in the National Severe Storms Laboratory. And they take that raw radar data and clean it up. And so you can see on the left side here, the images show a lot of ground clutter and false echo returns and blockage and other issues. And then WDT takes that information in and runs it through a number of mechanisms that clean up the data and pull in and make it look like what really is happening out there. So you can see the right side images show the cleaned up NEXRAD weather radar versus the left side images which show the ground clutter and so on. Now when we receive that data, we take that and do a number of other further QCing mechanisms to clean up the data and make it useful even further. And one of the things that we do that's very important is to take the NEXRAD weather radar reflectivity data, which tells us, relates how much rainfall is accumulating on the ground. So when you think about your nightly newscast, or if you're going online and looking at a weather radar loop, and you're seeing all the colors associated with that weather radar loop, and you're seeing greens and yellows, and they're telling you how much rain is falling where. Well, those images are showing a relationship between the reflectivity from the radar to the amount of rainfall that is accumulating on the ground, and that relationship is called the ZR relationship, or the reflectivity rainfall relationship. Now, what does all that mean? Well, what happens is the National Weather Service uses a couple of standard equations to fill in that relationship and produce an accumulation of rainfall. And here on this image, I have circled kind of the standard relationship for convection, which is Z equals 300 to the R to the 1.4. Now, what does that mean? Well, it just simply means, as the radar reflectivity comes back in, it applies those factors, and it produces an amount of rainfall accumulation for every given radar scan across a given area. Well, that's great to have that standard value, and it really gives you a nice high-level look at how much rain is accumulating in a given area. But unfortunately, storms don't have one size fits all. And in a given single storm environment, that relationship can vary widely at any given time and by storm type. And so what SPAS does is it takes the actual rain gauge information on the ground, and it relates it every hour to the reflectivity scans, and then it comes up with a best fit relationship to produce a much more reliable magnitude from the radar reflectivity. And this graph here is simply showing the black line is the best fit line for this particular hour, and you can see how much different that is than the standard National Weather Service blue line there. And that makes a big difference when you total that up over a whole given storm event as to how much rainfall the radar is saying is recording at any given location. So here's a couple things to look at that kind of relate what I'm talking to here. This is the National Weather Service one-day total precipitation analysis, and this incorporates both the raw radar returns for the whole United States put together in one image, along with rainfall adjusted reports from various river forecast centers across the country and so on. And they put out a product that's called the MPE, or Multi-Precipitation Estimate product. And you can see on this particular day from August 29th, 2011, this is when Hurricane Irene was making landfall along the East Coast, and you see very heavy rainfall out there, lots of reds and purples and whites, anywhere from 4 to 10 inches or more of rainfall in those locations. Now keep in mind that magnitude of rainfall as we look at the Hurricane Irene analysis that we did, and you'll see what I'm talking about there, where the NEXRAD weather radar amount of precipitation is often off by a factor of 10 or more. And we'll take a look at another example here. This is from November of 2006, when an atmospheric river event was producing very heavy rainfall along the west coast, along Washington and Oregon, rainfall amounts of up to 30 and 40 inches. Although the NEXRAD weather radar was only showing amounts of, say, 10 to 15 inches. Again, lots of problems with the magnitude, but the spatial coverage was done very well. Also, you can see here a pretty good storm moving through the southern plains of the United States, bringing up some pretty good moisture out of the Gulf of Mexico into Louisiana, Mississippi, and Alabama at this time, and probably some snow up towards the Ohio Valley. Another product that you can get from the Weather Service, which is very useful, is the River Forecast Center hourly precipitation products. And you'll notice on this map there's a lot of precipitation going on in several locations out there in the desert Southwest, southern Texas, the Southeast, up towards the Great Lakes and the Appalachians. But for some reason, nothing's happening on the West Coast. It's all grayed out over there. Well, how come that's the case? Well, one of the big limitations with the way the Weather Service uses these products is they don't have a way to deal with beam blockage and mountainous terrain in a real-time environment. And so one of the big advances of our SPAS program is that we have several processes that we are able to use to overcome that issue, where NEXRAD weather radar isn't available because mountains are blocking the radar, and or there just is other issues going on with the spatial coverage of the radar. Well, in our work, we can't just punt and say, oh, we're not going to do anything with those areas. We have to figure out a way to overcome that challenge. And the SPAS program, again, uses a combination of the Basemap technology and other information to do that. Another quick way to show how variable a given storm event is during its life cycle. The image on the bottom left there, where you see the rainfall amount and the moving best fit line, that's occurring every hour there. That black line is the best fit of the rain gauge data to what the NEXRAD weather radar is saying is happening there. And you notice how much that varies every hour there, quite a bit. Well, if you were just to use the standard ZR equation from the Weather Service charts, that blue line there, it's stagnant through the entire storm. And of course, that doesn't fit things very well. And the bottom right image shows the family of hourly curves versus the red line, which is the standard curve. And if you were to add up all those accumulations every hour, you're going to have a very different answer from what reality is if you're just to use the Weather Service's standard ZR equation versus that dynamically adjusted one. This is for Hurricane Gustav's landfall in September of 2008, by the way. So anyway, a pretty good tool there to really get a sense of how much rain is falling in between gauges. But again, remember, the little blue circles are actual rain gauge reports, and it's incredibly important that we have as many of those reports and as accurate as those reports as we can possibly get for any given storm event. Again, let's talk about what we do with our base maps when we're analyzing these storms in areas of complex terrain. This is a look at an area in western Colorado around the Untitled Plateau and the Grand Junction Montrose area. You'll see that left image there where the arrow is pointing in the circle. You just have several rain gauge reports on the ground, one around Montrose over towards Olathe and Delta and Cedar Ridge and Paonia. But if you don't have any way to tell what's going on between those gauges, you're just going to have a bunch of bullseyes and then some simple mathematic inverse distance weighting to spatially distribute that. But that's not how rainfall falls in the real world. It's not. It doesn't follow a simple mathematic formula. It follows its own patterns based on its interactions with the storm and topography and moisture inflow. And so the image on the right there shows how when we use a base map, that data on the left is corrected to better fit how rainfall would actually occur in this location given the underlying topography and the overall climatology of the region. And so you get a much more realistic pattern there where your highest rainfall amounts are occurring over the mountainous areas of the Untitled Plateau, and then you have lower amounts as you get towards the Grand Valley and the Gunnison River Valley around Montrose and Delta, and then higher amounts again up on the Grand Mesa around Cedar Ridge and so on. And that's the kind of pattern you would expect. And again, this is a very important way to look at things because you have to understand it's very unlikely you're going to have enough rain gauges around to collect the highest rainfall amount. And so you have to have some way to quantifiably distribute that rainfall between gauges. And you'll see here, if you just use the image on the left, your highest rainfall amounts would have been 3.8 inches in this one. While using the base map methodology to spatially distribute, now you're getting amounts twice as big, up to 6 and 7 inches. And of course, that has a big effect on the end result of a flood or other infrastructure design. Another look at this issue is areas where we have total beam blockage. So in other words, areas where that NEXRAD weather radar is blind. So for you CoCoRaHS volunteers that are living in regions like the Pacific Northwest or the Rocky Mountain States or Southern California, you see this all the time on your evening newscasts, or if you're looking at radar image loops, where there's areas that the radar just can't see. In this case, we're looking at the Pacific Northwest here in the Olympic Peninsula. The radar site north of Seattle is up on Camano Island at about 500 feet in elevation. Well, unfortunately, or fortunately, I guess if you live there, the mountains to the east, the Cascade Range, and then the mountains to the west, the Olympic Mountains, are much higher than that. And so as the radar is sending out its signal, it's getting blocked by those mountain ranges and cannot see, of course, through those. And so it's blind to what's going on in those areas. And the area circled in red there is one of the big spots where that radar is blind from Seattle. And so even though it's raining, it may not see it and not know what's going on. And so the base map methodology in SPAS is able to infill those areas. It knows that it's raining there. It's able to base that spatial distribution on a given climatology and say, okay, we know it's raining there. Based on how much it's raining in the other areas we're looking at, here's what we would expect it to be doing in that area where radar can't see. And that's on an hourly basis. On a total storm basis, which is the bottom left images and the bottom right image, same thing. So you look at the bottom left image, you see we had a big rainfall event there over the Puget Sound region, the Olympic Peninsula, and so on. And you can see the very extensive rain shadow effect that's so prevalent on the Olympic Mountains, where you have very heavy rainfall. In fact, it's one of the wettest places in the United States, up on top of the Olympic Mountains there around Mount Olympus in the whole rainforest. And very, very short distance to the east, you have the town of Sequim, where rainfall amounts are very dry, less than about 12 inches a year, and that big rain shadow on the Puget Sound. Well, on the west side of the Olympics, it's very wet, but if you only saw this image, you would think hardly any rain fell. And that's inside that red circle there. But when we do that SPAS analysis and we add the Basemap climatology, all of a sudden that dry spot on the west side of the Olympics gets filled in with what you would expect. So again, that's kind of demonstrating how that's employed in the real world. And again, it's very important to remember two things. One, if we can have actual rain gauge reports on the ground in those areas, i.e. ground truth, that helps us tremendously in filling those areas that we were missing or blind to data. And also that's very important for the users of that information, again, the hydrologists and engineers and others that are using that data. So the importance of accurate data. Again, we consider rain gauges to be ground truth, and so accurate data is very important. And the more CoCoRaHS observers we can get out there, the better. A couple of things happen when we're doing these SPAS analyses. One of them is we're constantly ingesting all the real-time rainfall information that we can get. That comes from the MADIS ingest system. That's from NOAA, and the folks up there at Boulder do a great job of getting that information out. And then in post-storm analyses, the National Climatic Data Center puts together all their QFeed information. But CoCoRaHS is not part of either of those data sets. And so CoCoRaHS becomes a very important tool that we use in our real-time quality control measures. It fills in the voids between all those official data sets. And one of the things that's very important, those official data sets are pretty widely spaced. So to have CoCoRaHS observers in as high a resolution and density as we can have, the better. And I know Nolan is always out there knocking on doors trying to get as many of us to sign up as we can. And believe me, that's incredibly important to do, and to get as many of you out there as possible. The other thing that's so cool about CoCoRaHS is that so many of you do such a great job of putting notes on your specific events, and we have big ones, and that's very, very helpful. You think about an event we had, I think it was back in June, and our observer down in Pensacola, Florida, had I think 21 inches of rainfall in a day, and noted the times that they observed the different tipping, or the rain gauge overflowing and emptying it and making those notes. That kind of information is incredibly important in our storm analyses. It really helps us to understand how and when the rainfall fell, and so please keep doing that. That's a very important aspect of the whole CoCoRaHS environment for us. A quick look at some of the products from our SPAS analysis. This first one here is a storm that we recently analyzed for a study that we're doing that's for a nuclear generating facility on the Mississippi River. Now this storm analysis is of a heavy rainfall event that occurred in the middle of March of 2008 in southern Missouri and southern Illinois. And you'll notice the total storm rainfall image is what we're looking at there. This analysis included over 1,100 rainfall reports from all the sources that we could get. But what you'll notice on this image, all those purple circles, those are CoCoRaHS observations. And so you can see on there how important those are in helping to fill in the gap and give us more information to use. We can never have too many accurate rainfall reports, and in this particular example, you see how many CoCoRaHS observers really helped out in quantifying the rainfall. Now, don't feel bad, Arkansas, when this analysis was done in 2008. Arkansas wasn't online yet with CoCoRaHS, so if we had done this again now, we'd have a lot more purple circles there in Arkansas. So we got to keep getting you guys going. Another thing to think about here, so let's talk about some of the big storms that we've analyzed and take a look at what they look like after a SPAS analysis is completed. So when we do a SPAS storm analysis, we produce several pieces of information that tell us things like not only how much rainfall at a given rain gauge, but how much rainfall fell over an entire storm domain, say 100,000 square miles or an entire county. And then, of course, we want to know how much rainfall accumulated in time and space. We'll look at things like mass curves and those depth area duration tables that I talked about, and that gives us that three-dimensional look at the storm and really helps us figure out things for flood design, flood control, hydrologic calibration, you know, being able to determine a given flood event and so on. And having that rainfall and that three-dimensional look really gives us that information we need to come up with those pieces of data. And also, it gives us a nice objective way to spatially compare storms. I mean, it's pretty easy to say at any given location, hey, I had 10 inches of rain today, and in 1926 that spot had 11 inches of rain. Well, that's great for that spot, but what does that mean for an overall given storm environment? That 10 inches of rain you had may have been a much bigger overall storm than that past event, but if you don't have a three-dimensional look, you really have no way to understand that. So let's walk through some of the big ones and also talk about some of the storm types, some of the cool types of storms that occur across the U.S. and the resulting rainfall. One of the first ones we'll talk about are upslope thunderstorms or front range thunderstorms. These are close to my heart here in Colorado, and of course, very important for CoCoRaHS because without Fort Collins, July 1997, CoCoRaHS might not exist. The other big one, of course, that has occurred here in Colorado is pretty infamous, is the Big Thompson Canyon flood of July 1976. Now, we've had an opportunity to analyze both of these storms using SPAS for a study we're doing for the state of Wyoming, so let's take a look at some of the results. First of all, for the Fort Collins storm of 1997, a couple of images of the aftermath there, extreme flooding there on Spring Creek all around Fort Collins, especially the west side of town, and into the Colorado State campus. Nolan, of course, has a lot of firsthand experience with that, can give you a lot more information, but a devastating event for that location. And it has been looked at in a lot of ways in the past, but this is the kind of the first fully integrated look at the storm with a full depth area duration analysis, incorporating NEXRAD, weather radar, and so on. Kind of an interesting couple of things to note here. The heaviest rain, of course, fell in a north to south orientation, anchored against the first upslopes of the Rocky Mountain Front Range there west of Fort Collins. And that's kind of what you would expect when you get a moisture inflow from the east-southeast encountering the Rocky Mountain Front Range oriented north to south. It's going to help to anchor your rainfall and your thunderstorm development, and that's what happened in this situation. And you can see over western areas of Fort Collins some very heavy rainfalls, up to 14 and 15 inches in a couple of spots there. What does the resultant depth area duration table look like with a storm like this? Well, the highly convective storm with a lot of rainfall falling in a short period over a small area size, this is what you would look to see. Notice that at the smallest area sizes there, you have very heavy rainfall. In this case, at 24 hours, at 1 square mile, about 12.5 inches of rain. But that amount falls off very quickly as you get to larger area sizes. And by the time you get to about 500 square miles, it's actually not that big of an area, you're already down to only 3 inches of rainfall. So very highly localized, heavy rainfall event. And the depth area duration curves reflect that as well. You see those high point rainfall amounts with the red squares there, almost 13 inches. And then it falls off very quickly as you go up to larger area sizes. Again, this is a mass curve of the rainfall at the storm center, and this gives us information on how much rain fell in any given hour during the storm analysis, and also how much rainfall accumulated over that time. And you can see some pretty heavy bursts of rain there, especially between hours, say, 33 and 37. In fact, there at about hour 36, you had almost 5 inches of rainfall in 1 hour. And that's why we had such devastating flooding on Spring Creek and other areas around Fort Collins. It just wasn't able to handle that heavy of rainfall on a saturated ground, and it all ran off very quickly and caused those problems. The other storm that we're talking about for the upslope thunderstorm type event, of course, is the Big Thompson Canyon flood of 1976. A number of reports have been done on this flood, and this image here is from Jarrett and Costa. Bob Jarrett does a lot of great work on paleo flood work in and around the Rocky Mountain region, and they produced this fact sheet which kind of describes the various parameters that were going on to cause this big flood. Some of the important things to note, just like the Fort Collins storm of 97, you had very deep moisture flowing out of the Gulf of Mexico on easterly winds and pushing up against the Colorado mountains and the first upslopes. So you had that forced ascent, that forced rise that really helped to push that moisture high in the atmosphere and convert it into rainfall. Also, you had very weak winds aloft. Normally in Colorado, when we get these big storms popping up in the summertime, they move off very quickly from west to east and don't really cause too much of a problem because they aren't over one given area for a very long time. But in this case, the winds were very weak and the storm sat over the same area for an extended period. And to make matters worse, the area that it rained on there on the Big Thompson Canyon flood is all a lot of granite rocks, very impervious soils, and so as the rain fell, it washed off and ran off almost immediately into these very deep and narrow canyons and funneled it right through that region. And of course, that led to a lot of devastation, unfortunately a lot of lives lost, and just a lot of bad flooding. And these scenarios, of course, are still happening and could happen again. But let's take a look at the SPAS analysis of that event. A pretty similar footprint to the Fort Collins storm of 1997, where you have that north to south oriented rainfall, heaviest rainfall location, again anchored to that high mountainous terrain there west of Boulder, and caused a lot of rainfall in a very short amount of time. And so you'll notice on the depth area duration chart, very much like Fort Collins, we have a lot of rainfall at the shorter, smaller area sizes and in pretty short duration. So at 12 hours, you already had 10.5 inches of rain in about a square mile. But again, once you get up to about 500 square miles, it falls off very quickly and not nearly as much rainfall. So these types of storms cause a very high peak flood, but the volume of rainfall isn't nearly as big as some of the other types of storms we're going to look at in a minute. Again, the mass curve for Big Thompson Canyon, a lot of rainfall in just a few hours, again up to 4 inches of rain in 1 hour. And again, if you think about up at 8, 9, 10,000 feet, that's an incredible amount of rain and moisture to make it up into that high of the atmosphere and in the thunderstorm environment. And all that fell in a very short time with not much else happening over the rest of the area. Another pretty cool type of storm that affects really all the country, but is really especially well known along the West Coast. They used to be called Pineapple Express storms, and they've kind of evolved to be known as atmospheric rivers now. A prime example is what we're going to look at here is one from November of 2006. Well, let's first take a minute to talk about atmospheric rivers and or Pineapple Express storms. There's been a lot of research done on these events, especially in the last 10 years by people like Neiman and Rolf and Diedemeyer and Larry Schick. Did a lot of work on the West Coast because these storms are the cause of all the major floods along the West Coast, basically from British Columbia all the way down to Southern California. Now, one pretty interesting thing that they found about atmospheric rivers is that they move about 90% of the water from the equatorial regions towards the pole regions over the Earth's surface. But they're very narrow tongues of moisture that are doing this, only say a couple hundred miles wide, a couple thousand miles long, and that these are occurring on the Earth around the globe at any given time. Almost, there's a few of them occurring along the globe at any given time. So there's a phenomenon that's kind of always occurring that we've really been able to understand and study since the advent of satellite technology. And this image we're looking at here is pointing out that at this particular time, this is back in April of 2008, there were several atmospheric rivers occurring all throughout the globe. And these are these long filaments of moisture that are showing up on the satellite image. These are what are called integrated water vapor images from these satellites. So it's kind of giving us a look at the amount of moisture throughout the atmosphere, from the top of the atmosphere down at any given location. And these atmospheric rivers are, like they're called, basically rivers of moisture that are streaming up from the equatorial regions towards the equator, towards the poles. And when they act with the right environment, say a cold front coming down from the Gulf of Alaska along the West Coast, it taps into this huge moisture source, focuses it on one area, and it's kind of like having a fire hose pointed at your location. You get these very heavy rainfalls over a long period of time. Here's another look at that November 2006 atmospheric river. Again, the purples and reds and oranges indicate the higher levels of integrated water vapor, while the blues and greens are the lower amounts. And again, you can kind of see there, just like a river crossing the Hawaiian Islands, going up to the Eastern Pacific and slamming into the west coast of Washington, Oregon, you have this tongue of moisture, this river of moisture feeding the storm as it comes on shore. And what happens in these big flood events along the West Coast, when that tongue of moisture is able to feed into the same region and kind of sit there for a several-day period, you get these devastating floods. And that's what happened here in November 2006. And as I mentioned, the research done by Neiman and Schick and Diedemeyer and Ralph, all of it shows the same story. In places like the West Coast of the United States, all the big flood events are associated with atmospheric rivers. And so it's imperative that we know and understand how these happen, when they happen, where they occur, how often they occur, because it causes an immense amount of damage and problems in these areas. And on the other end of that, when we can do a SPAS storm analysis of these events and get a picture of how that rainfall falls in space and time and magnitude, that really adds to the data set and the scientific understanding. And on the lowest level of that, of course, is the importance of our CoCoRaHS observations in helping to understand these rainfall events. So this example here in November 2006, you see 3 rainfall centers that we looked at with SPAS that held more than 35 inches of rainfall. Pretty incredible amounts of rain as that atmospheric river came ashore and interacted with that slow-moving front coming out of the Gulf of Alaska and really enhanced the rainfall. Now, other factors along the west coast really make things even more dramatic. You have the coastal range of Oregon, the Olympic Mountains there of Washington State, and the Cascade Mountains. Those are all orographic terrain that help to enhance and focus the rainfall amounts in those given areas. In this particular case, that zone number 3 there, up around Stevens Pass, Washington, east of Everett and Seattle, the highest rainfall center we found was up around the town of Index. Beautiful town up there if you ever driven across. Maybe you get a chance. Great, great scenery. But in this case, it had a lot of rainfall, almost 40 inches of rainfall in 144 hours. But this occurred at a location where we did not have any rain gauges on the ground. And so the rain gauges we had around there, again, and the Basemap technology, were able to come together, and then we're able to adjust that ZR relationship in the NEXRAD weather radar and come up with a storm center that was much larger than anything actually recorded at a rain gauge, but was also reflected in the record flows on the Snohomish and Skykomish rivers in that region. So again, all those pieces of data we've talked about come together to make these storm analyses complete and so informative. Again, the depth area duration table for this type of storm where you have a lot of rainfall over 70 days, over 7 days over a large domain, and you can see the difference in the depth area duration table. You have almost 40 inches there at 144 hours, but even as you get out to say 5,000 square miles, you're still well over 16 inches of rainfall. So a lot of heavy rain, not only in a peak, but also in a volume. And the curves associated with that show that very nicely, where the curves do not fall off nearly as quickly from right to left as you go up into area size. And again, that tells an engineer and a hydrologist that not only are we getting heavy rainfall peaks, but we're getting a lot of volume of rainfall. And depending on the river system you're dealing with or the infrastructure you're dealing with, that's a very important piece of information. Here's a look at the mass curve with that November 2006 storm. And again, you can see the extended period of rainfall, a number of hours of over a ½ inch of rain. But one thing to notice, the scale on the left only goes to 2 inches. And so we didn't have any of those single peaks of, say, 4, 5, or 6 inches like we get with thunderstorms. We just had a number of hours there with a 1 inch rainfall or a ½ inch rainfall. And then combine that, of course, with the time of the year and location, you have melting snow as well. And you begin to get a lot of runoff into your river system. Now, atmospheric rivers don't just occur along the west coast. We've also found that they occur in places all over the globe, and in this case, the ones that occur in the Midwest and the East Coast have also been given the name of the Mayan Express. A storm that fed into the Mayan Express was the Nashville, Tennessee 2010 storm in the early part of May, which caused a lot of devastation around Nashville. Now, why are they called the Mayan Express? Well, the atmospheric rivers in this region happen to pull their moisture from areas around the Caribbean and Central America and northern South America and the intertropical convergence zone in that region. And they pull their moisture up to the Gulf of Mexico and along the states bordering that area and along the East Coast. And so that's why they get the Mayan Express name. But they're all the same type of event, that atmospheric river pulling moisture from the equator towards the poles. And you can see those two images there showing that stream of moisture, the red and purples coming right up over Central America, right up over the Gulf of Mexico, and right into Nashville in this case. And when you combine that with a front coming across the region, you have some big problems. So here's a look at the SPAS analysis of that Nashville May 2010 event. And you'll notice we had a couple of what are called mesoscale convective complexes flowing from west to east along a basically stationary front right across Tennessee. And that interacted with that huge amount of moisture coming up with that atmospheric river out of the Gulf Coast and produced a lot of heavy rainfall and a lot of devastation right around Nashville. You had that rain basically extending from all the way from Memphis up to the Knoxville area, and a lot of rainfall of over 15 to 16 inches in that whole entire range. So what did the depth area duration table look like with that storm? Well, as you might have guessed, with a lot of rainfall over a large area over a couple-day period, not only did you have big rainfall amounts at the small area sizes, but again, even when you get up to around 20,000 square miles, you're still up over 10 inches of rainfall. So you had these huge volumes of rain affecting the Tennessee River system and causing a lot of problems for all the dams and reservoirs in that area. And then the curves associated with the depth area duration, same thing. They don't fall off very quickly as you go from the smaller area sizes to the larger area sizes, and again, showing there's a lot of volume under those curves and a lot of runoff. The mass curve associated with the storm showed that there were really two big bursts of rainfall. One in the initial period, which set some rainfall records at the Nashville International Airport, and another big burst towards the end of the event. And of course, that first event served to saturate the entire area and get all the reservoirs up to full capacity. And then you had that second big event come in, and that's where you had a lot of big flooding problems occur because everything was already full and saturated in the area. Another atmospheric river to look at, we've just been talking about how atmospheric rivers are creating all these rainfall problems. Well, if it's cold outside, it doesn't rain, but it'll snow instead. And so one of the bigger atmospheric rivers that have occurred recently in the wintertime was in February of 2010. And for any of our CoCoRaHS observers that were living along the East Coast or New England during the winter of 2010, certainly remember that as one of the snowiest, if not the snowiest on record. And one of the reasons with that mega storm, super snowmageddon, that occurred in early February of 2010, and that was fed by an atmospheric river, which you can see there coming right over Central America from the equator, right over the Yucatan Peninsula, western Cuba, southern Florida, and then right up the East Coast. And with the cold air mass coming off of out of Canada interacting with a high level of moisture, the result was one heck of a lot of snow, and piling up snowfall records all over the place from Baltimore to D.C. to New York City and Philadelphia, and adding to those seasonal totals, which set some new records in many of the areas out there. So very important phenomena, those atmospheric rivers, at transporting huge amounts of moisture from the equator up to the mid-Atlantic and equatorial region, or to the polar regions, and so on. And that's something that's occurring on a daily basis around the country. All right, on a much smaller scale, we have what are called mesoscale convective systems or complexes. And these are those big areas of thunderstorms that roar through the Midwest and Central Plains in the spring and summer and produce a lot of heavy rainfall in a short time frame over a smaller area size. Here's an image of a typical mesoscale convective complex. This is over from the summertime of 2010 here. And you can see the image has kind of the classic image of what we would look for. That's a circular shape about the size of the state of Iowa, very cold cloud tops where those thunderstorms are really building up and forming. And how do we know that? Well, the areas on the image that are in red and black and white signify very cold temperatures, and that usually means very high cloud tops, very high up in the atmosphere. And that signifies a very strong thunderstorm, usually with very heavy rainfall, sometimes with large hail, maybe a supercell thunderstorm with potential for tornadoes and so on. This is a classic signature of a mesoscale convective complex that you'll see so often in the Midwest. And again, these produce very heavy rainfalls over short durations and small area size. And a very good example of one of these types of events is the Twin Cities superstorm of July 1987. We analyzed this storm as part of some work we're doing for Ohio, where this storm produced 2 rounds of very intense mesoscale convective systems rolling across right over the Minneapolis-St. Paul downtown area. And again, you notice how the orientation here of the heaviest rainfall is basically west to east, because the overall flow of movement of the storm, again, is moving it from west to east along the jet stream pattern, but it's also interacting with a front that was sitting over this area, much like that Nashville 2010 storm. And so the focusing mechanism was right over Minneapolis and, of course, caused a lot of devastating flooding and a lot of problems. The depth area duration table associated with this storm, like the thunderstorms we looked at for Fort Collins and Big Thompson Canyon, a lot of heavy rainfall at small area sizes and short durations. So at 6 hours, at 1 square mile area size, we had about 11 inches of rainfall. But very quickly, as we get up to 500,000, 5,000 square miles, our rainfall amounts fall off very quickly. So again, this caused a very high peak runoff, a very quick runoff of flood event that went through very quickly and caused a lot of damage. And as you expect, the depth area duration curves with this type of storm fall off very quickly as you move up into the area sizes. And the mass curve shows that almost all the rainfall fell in about a 6 to 7 hour period there, and you had 2 hours there where you had more than 3 inches of rain in a single hour. And if you can imagine up in the upper Midwest, boy, that's a lot of moisture, a lot of rainfall for a place like Minneapolis. Another storm type we're going to look at that's pretty cool and unique to the United States is known as the North American monsoon, or also known as a Southwest monsoon. And of course, This has its largest effect over places like Arizona and New Mexico, but also brings a lot of moisture in the summertime all the way up into Utah, Nevada, Colorado, Wyoming, and so on. And so it's very important to understand how this mechanism works and what the storms look like that are associated with it. One of the big events we'll look at from this type of pattern is a thunderstorm event that occurred around Roosevelt Lakes area of Arizona, just outside of Phoenix in the foothills in September of 2003. First of all, though, let's take a look at what the monsoon pattern looks like across the United States. Generally what happens is we get a nice area of high pressure that builds up over the southern Great Plains, Texas region during the spring and early summer, usually starting around June. And remembering your old meteorology classes, air flows clockwise around high pressure in the northern hemisphere. And so you have this clockwise flow around that high that's bringing moisture out of the Gulf of Mexico, the Gulf of California, and the eastern Pacific Ocean right up into the Rocky Mountain region in the desert Southwest. At the same time, you'll usually have an area of low pressure that'll form a thermal low out over Southern California and Nevada. It gets so hot there that the air is so efficient at rising that you have low pressure at the surface, so you get this thermal low out there. And then the airflow around that low pressure system is counterclockwise in the northern hemisphere. So between that area of high pressure to the east and low pressure to the west, you get this nice constant flow of moisture from the south right into the desert Southwest. And again, this starts to set up around late June and continues all the way through September in most years. It doesn't form the same way every year, which is what these three patterns are showing. Some patterns are more favorable for heavier and consistent rainfall in the Southwest than others. But generally, you get the same regime, and often it produces some pretty good thunderstorms and rainfall in a consistent manner in Arizona and New Mexico. So don't believe that old moniker about, oh, it's hot in Arizona, but it's dry heat, because in July and August and September, it's not always that dry. It could be 110 degrees with some pretty high humidity, too, and trust me, that's not that much fun. So taking a look back at that Roosevelt Lake storm of September 2003, a very localized thunderstorm event right near a big reservoir there, Roosevelt Lakes Reservoir, outside of Phoenix. So you see the rainfall footprint there in our SPAS storm analysis. We had up to 10 inches of rainfall in that little area of white in a very short time period. But because a lot of the areas of the desert Southwest are pretty, population isn't real dense, we don't have a lot of rain gauges around the area. And so if you don't have a rain gauge at a given storm event, we might not know it ever happened, or we certainly might not know how much rain fell. And so you can see here there are some real hard to see, but hopefully you can see them, blue circles and red circles. Those are our rain gauge locations that we were able to use in this particular storm analysis. The red circles are hourly data, and the blues are daily data. And this again points out to the need of having more and more stations. The more of those rain gauge locations we can get reporting data for a given storm event, the more accurate that analysis is going to be. And this was a pretty devastating flash flood in the area. And these are the type of flash floods that occur so often in the summertime in the desert Southwest, where the more data we can get coming in that tells us it's raining somewhere and how much it's raining, the more useful it's going to be for emergency managers and flood response and everything else. So keep those coming. Now, as you might have guessed, the depth area duration table associated with the storm analysis shows that same pattern that we see with the thunderstorms. Very heavy rainfalls at small area sizes. In this case, 11 inches of rainfall in just 5 hours at around a square mile, but falling out very quickly to less than 2 and 3 inches as you get towards 1,000 and 2,000 square miles. And again, those curves show the same pattern, falling off quickly from right to left. You'll notice the mass curve shows that we had, in 1 hour there, we had almost 6 inches of rainfall in that area. And if you can imagine a normally dry area there in Arizona, that rain is going to run off very quickly and cause that very, very high flash flood in a very quick time. The last type of storm we'll take a look at here is hurricane landfall events. We're going to concentrate on the Hurricane Irene event here on the East Coast, but of course these are relevant for all areas along the Gulf Coast and the East Coast. And of course we're watching the storm out there in the Caribbean right now, which may be affecting Florida and the East Coast towards the beginning of next week. And may have a very similar looking pattern to what we saw with Irene, if the models are correct on that. So let's take a look at Irene. This was a pretty cool event for us as meteorologists that are studying extreme storms. Of course, not so fun if you were affected by it, but from out here in Colorado, it was nice to follow. One of the neat things that we got to do with the storm is do an on-the-ground bucket survey, and I'll talk about that in a minute. First of all, though, let's take a look at the path of Irene. Very typical path for a late August storm, Cape Verde type season, where it starts to form over in the eastern Atlantic off the Cape Verde Islands, moves around the area of high pressure that's normally centered around the Bermuda High, off towards the Caribbean Ocean, or Caribbean Sea, going through the West Indies and the British Virgin Islands up towards Puerto Rico and Dominican Republic, and then curving around that high off the coast of Florida. Now, unlike most storms, though, it didn't curve back out to sea around Bermuda. Instead, it decided to move a little bit further to the west and move up to the west to the east coast of the United States, and that's where all the damage occurred. So as I mentioned, we got to do a really neat thing here at Applied Weather Associates, and we're able to do an actual on-the-ground bucket survey of the storm. This is something that had been done consistently by the Weather Service and Corps of Engineers when they were doing their past storm studies, but stopped being done in the 1970s. And so almost nobody's been able to do this since then, where you actually go on the ground, go to the location where the heavy rainfall occurred, and actually talk with people, interview local residents, see what happened, see what kind of rainfall amounts were captured in non-conventional ways, like, say, just a bucket that was left outside, or a tray, or a horse trough, or whatever it might be. And you're able to use that data with all the other rainfall and rain gauge and radar information and come up with a very, very distinct picture of the storm, and often come up with rainfall amounts that would never be known otherwise in the official record. So the image we're looking at here is a total storm rainfall map from our analysis of this storm using SPAS. And the outline there in black is a drainage basin up in the Catskill Mountains of New York where the heaviest rainfall fell. And we'll take a close look at that and take a look at some of our bucket survey information and tell you how we used that and how we conducted that bucket survey. And you, as a CoCoRaHS observer, if you're in an area where there's a big rainfall event like this, it's very likely that if somebody was to do a bucket survey, we might be knocking on your door and asking for information. So kind of keep that in mind. Also important to why we keep those good notes on those big events. So the depth area duration table for Hurricane Irene kind of showed what you would expect here, a combination of both a widespread rainfall with heavy rainfall picking up big volumes, as well as some convective elements where you get some peak rainfalls over shorter area size and smaller durations. And so you'll notice here at the 18-hour duration, at the 1 square mile area size, we had over 23 inches of rainfall. And we still had pretty decent rainfalls, even out around 1,000 and 2,000 square miles, up 8, 9, 10 inches. So as you would expect with a tropical system where you have a lot of moisture, you have it affecting a larger area, but you still have a lot of convection involved, you kind of have that hybrid-looking depth area duration table and curves. Now the mass curve of the storm showed that we had some pretty steady rainfall over a decent duration here, several hours, about 12 to 18 hours of rainfall, upwards of over 1 inch per hour at the storm center. So a lot of rainfall occurring, which led to both a very high peak flood and also some high volume flood in this river system, the Schoharie River system, which feeds into the Hudson River, and also on the south side feeds into the Delaware River Valley. Devastating flooding occurred with Hurricane Irene. A lot of areas, the Schoharie Creek area, normally you would have one narrow band of the Schoharie Creek going through that valley. Well, the entire valley was inundated, lots of damage and lots of destruction. Some other pictures from the Albany National Weather Service office here providing a lot of flooding and a lot of damage flowing right through the streets of Tannersville there up in the Catskill Mountains, and just a lot of devastation. Now, one of the cool things that we got when we did this bucket survey was some very, very interesting and very diligent observational notes. Now, this lady, Karen, who took these notes on the storm, you can see her there, I'll go back to that in a second, did a great job of diligently recording how much rainfall fell in her increments here, where she would go out. I mean, you can imagine it's raining 4 inches an hour for the last 4 hours. You're going outside, checking the rainfall, taking those measurements in the dark of night while things are flooding and all this disaster is happening around you, yet she still is going out there and giving these diligent observations. And this type of data is incredibly important for our SPAS storm analyses. It tells us not only the magnitude of the rainfall, but the timing of the rainfall. And this is at a location where there were no rain gauges, at a location where the NEXRAD weather radar coverage wasn't that great. And so to have this information from such a dedicated observer is so important. And she's not even in CoCoRaHS, so we've got to work on that and get her in there. But you can see the rain gauge that she used here. And even though it's not the most ideal rain gauge in the world, and Nolan would probably have a lot of fun trying to help her out with her sighting there and everything else, it still is useful. That data can still go into the overall process and when it's married up with all the other data we have, is able to be QC'd and used just as well as anything else. So you can see all the work she must have gone into to go out there and change that gauge every few hours and empty it out when it was filling up and overflowing probably 5 or 6 times during such an extreme event. Some of the pictures we got from our ground survey there, our bucket survey, this is a month after the event occurred. We were out there at the end of September, and this rainfall event occurred at the end of August. Still lots of devastation, still roads closed, still things just unimaginable. And you can see some of the damage, their houses off their foundation, vehicles totally destroyed and bent around like toothpicks with, just a mess, basically. So some of the results of our bucket survey, and by the way, I got to give thanks to Patrice Sutter and Doug Holtstrand. They were the 2 AWA employees out there on the ground doing all the work for that whole weekend, did a great job of getting out there and talking to lots of people, and they're both CoCoRaHS observers as well. Anyway, so some of the results we got from our bucket survey are listed in this table here. You'll notice a lot of the notes we have, a lot of them are estimations, a lot of them weren't taken into rain gauge, and so on. But one of the coolest stories that Doug and Patrice relayed to me when they came back and we were going through the data was of an observer that they just named Mountain Man. He's on the very bottom there. And what they found was when they went and talked to this guy, he had lived there forever, 20, 30 years in the same place, had observed lots of storms and lots of heavy rainfalls in the area, and watched how they affected the local environment, and specifically the creek that ran by his house. And so when they interviewed him, he told them that based on the level of the stream and where it got to on the rock in the stream, he estimated about 22.5 inches of rain had fallen. Now, normally when you hear something like that, you might laugh it off or, oh, okay, thanks, great, it's nice to know, and probably not put much credence in that value. But a couple of things happened when we looked at that information. First of all, that 22.5-inch value would have been our highest reported observation. So it's very important that we make sure that we QC that and see if that was accurate or not, because if it is, it's going to have a big effect on the overall storm analysis. And the other thing was, well, not really knowing much about this or if it was reliable or not, we thought we would test it out in a couple of ways. And so when we ran the SPAS analysis, we ran it without that observation at that point, and then we also, of course, ran it again with that observation included. And what we found was that guy's just observation of looking at the stream level and knowing his local environment was incredibly accurate. It was within a half an inch of what was actually showing up in our storm analysis, where we're using hundreds of actual rain gauges and NEXRAD weather radar and everything else. All these official QC data sources verified and validated this guy's report incredibly well. I mean, it was amazing to think that from the way he analyzed it and the amount of rainfall that he estimated to have occurred was actually so accurate. So a very valuable piece of information and a great story from a resident who had lived there forever and just really was paying close attention to what was going on. But another guy, we need to get signed up for CoCoRaHS here to really help us out. And so how does all this look when we started to put this Hurricane Irene bucket survey, ground survey information together into one cohesive piece of information and run it through the SPAS storm analysis? Well, what we saw here is if you just took the National Weather Service's River Forecast Center MPE product and looked at the rainfall in that area, you came up with values around 16 to 17 inches. And that's what we're showing on this map here, the colorized rainfall contours in the area we were looking at here. I know it's hard to see a little bit under the callouts, but under some of those callouts you'll see some whites, some pinks and purples, and those are signifying 14, 15, 16 inches of rainfall. A lot of rainfall, no doubt, but not as much as actually occurred. So when we go on and we do these bucket surveys and we add in the CoCoRaHS data, these pieces of information that often are not entered into the official forecast, but we use them in our SPAS analysis, the picture changes quite a bit. And you'll notice there 16 to 17 inches is a lot less than was observed by a lot of the people in these areas where you're getting 18, 19, 20, 21, 22 inches. And so when you put all that data into our SPAS analyses, you get a much clearer picture and a much more realistic picture of the storm's magnitude, its spatial distribution, and so on. And that's very, very important, as I mentioned, for infrastructure design and for runoff modeling and flood hydrology. In this case, you see our SPAS analysis, we're showing over 22 inches, that 22.5 report by the Mountain Man, upwards of 23 inches when you calibrate that to the radar, while the Weather Service's products were showing 16 to 17 inches. And I want to make sure you understand here, the Weather Service does a great job. I'm not trying to make them look bad in any way. Their charter isn't to do these kind of storm analyses in these ways. They're They're trying to use their information in different ways, so it's not expected that their analyses would be able to be as accurate as the SPAS analysis, because we have time to go back and put in all these pieces of information and to calibrate the weather radar on an hourly basis. They're not doing that, so it's not surprising the values are different. But it's interesting to see the magnitudes and how much difference that makes, and then realizing how important that is for the users to know that you have accurate rainfall data. And when we talk about that, one of the uses that is this data is used for so often is called probable maximum precipitation. This is one of the main things that Applied Weather uses our storm analysis for. Now, probable maximum precipitation is a theoretical depth of rainfall. So it's technically defined as the theoretical greatest depth of precipitation for a given duration that is physically possible over a given storm area at a particular geographic location. That's a definition from the Weather Service's Hydrometeorological Report 59. And so this is a theoretical upper limit of the most amount of rainfall that could possibly occur at any given location at a given time of the year. So it's an amount of rainfall that should never be exceeded. So the Weather Service provided these values through what are called hydrometeorological reports through about the 1990s. But just like the storm analyses that they're based on, they stopped. They no longer do them, and they no longer support them, and they no longer provide any guidance. They do provide the documentation, but they don't provide any guidance. And so all of these reports have become very outdated. Most of them didn't, well, none of them recorded any or used any NEXRAD radar data in their analyses. Very few of them had any computer interactions such as GIS in their analyses. And of course, the newest storms that were used in them for most of the country were the 1970s. So they're very outdated. And so as users of this information, dam owners, hydroelectric power producers, nuclear facilities, and so on, as they begin to build new facilities or relicense their facilities or to ensure and inspect that their facilities were still safe, they begin to realize that the documents they were using were very outdated and in need of updating. And so that's where AWA came in and started to fill in that void and in conducting these probable maximum precipitation studies. And again, as I mentioned, out of necessity, we had to update that storm database to fill in all that gap that was missing and be able to update these probable maximum precipitation data sets with current and updated information. Here's a quick look at the National Weather Service HMR coverage across the country. You can kind of pick out where you live and see what HMR covers your site. They are available for download for free if you wanted to read through one of the documents and see what it looks like for you and the rainfall analysis that were used and the amounts. Basically, everywhere east of the Continental Divide from 130 degrees longitude eastward is covered by HMR 51, and then there's a series of HMRs along the west. So what is a dam owner to do if they have a problem or they need to redesign? Well, that's where we started to do these studies. And the first one we did was in 1993, and it covered the states of Michigan and Wisconsin, and it was for the EPRI Energy Research Institute, and it was run by the Federal Energy Regulatory Commission, FERC. And then since then, we've done more than 30 more studies since that time frame, mostly in the last 10 years, and we've really begun to fill in the void across most of the country for that missing data set and then updating that whole data set of the HMRs. And this image just simply shows the location of the various projects that we've completed and are in progress. Right now we're doing the entire state of Ohio, the state of Arizona, and the states of Wyoming. And so those are, and we've also completed the state of Nebraska previously. And so this data set is getting updated piece by piece as a user kind of needs that information, and will continue to do so going forward. But the whole foundation of being able to do these studies is to have those storm analyses complete, and to have a complete storm analysis, you need that accurate rainfall data on the ground. Quick look at some of the results of those PMP analysis to give you a sense of what PMP rainfall looks like. This is results from our state of Nebraska study. This is for the 24-hour duration at 100 square mile area size. And what you see here are some pretty cool things. I mean, for the most of us, when you think about Nebraska, you think about a pretty flat state, not a lot of variation. I mean, I've driven across Nebraska. It doesn't seem to change much as I go from Scottsbluff to Omaha. But in the world of meteorology, there's a big difference in Nebraska. As an example, our PMP shows that at 24 hours, 100 square miles, we had rainfall values around 20 inches down in the southeastern corner of Nebraska, while in the western and northwestern parts of Nebraska, as you get towards Wyoming and Colorado, those values fall off quite a bit, down to 15 inches or so. And that's explained by the meteorology pretty well. You have a lot less moisture making it consistently into western Nebraska, especially on a longer duration and larger area sizes as compared to southeastern Nebraska, where you're much closer to your moisture source. Also, the elevations of southeastern Nebraska are less than 1,000 feet along the Missouri River. But while you get out to western Nebraska, you get up to 4,000 feet, quite common, and so you also have less available moisture in the atmosphere as well. And so these kind of patterns show up very distinctly when you do these kind of storm analysis and storm studies, and that really affects your final PMP values. Another quick look at what PMP looks like. This is called a depth area chart, and this is a pretty neat thing to look at when you consider the storm analysis aspect of things. Each of these individual lines is one big storm that we've analyzed for a specific study. There's about 19 of them here, I think. And so what we do is compare that to the HMR values for this given location, and also do what's called an envelopment of the data. So all these curves are plotted on this depth area chart where you have precipitation values on the y-axis and area size on the x-axis. And you put all these storms onto one plot, and then you envelop them. That's what that black line is there. And so that basically draws a line that ensures you've captured the largest values at every area size as you go up there. And so what you're doing in essence here is combining all these distinct storm events, these biggest of the biggest storms that you've maximized and moved to this location, into one design storm. And that design storm becomes your PMP storm. And that's how you get to that theoretical upper limit, where you've combined the biggest of the biggest storms that have ever occurred in the period of record for a given location. Then you maximize them by making them as big as they could have been had all the meteorological parameters been perfect when that storm occurred versus how it actually occurred. And then you plot them together and you make them as big as they can be. And what you see on here is one storm is driving that curve at the 10 square mile area size, a different storm is driving at 100 and 200 square miles, and then a third storm is driving from that point upward. And so you're combining three different storms into one design storm to drive your PMP values. And that's a way that you kind of come up with that theoretical upper limit of rainfall. In this particular case, this is a result of that analysis for this basin. You got values of 16 inches in 6 hours. This is in the Fort Worth area of Texas. So you can get a lot of rainfall there. At 24 hours, you had 28 inches, and at 72 hours, they're almost 33 inches. Now you compare that to the values from the HMR document that was valid for that area, and you notice that the person that's using this information, okay, we had this old document, HMR 51, the newest storm that was used for this area in that document was from the 1950s. So how much has changed over that time if we were to relook at this? Well, you can see that the reductions from HMR 51 for this particular case range from about 7% to 20%. And so if you're a dam owner or responsible for a reservoir or flood hydrology or other infrastructure, to know that your values are now based upon a larger storm data set, are much more accurate, include the latest technology and meteorological understanding, and then to have those values be about 15 to 20% less than what you had to design for before, that's some pretty good news to you. And so you're happy to get that information, and it helps you really understand your problems and deal with the infrastructure you need to deal with. So hopefully after all the stuff we went through today, you have a pretty cool understanding of the storm analysis work that continues to go on today in the private sector, and what was done in the past in the public sector, how that information was used, how the storms are analyzed, how it's put into use in practice, and most importantly, hopefully you have a pretty good understanding of just how important it is to have as much data as we can get from CoCoRaHS observers, and to make sure that data is as accurate as possible and includes notes on extreme events and so on. Hopefully you get a good sense of just how much we use that data and how important that is in the end result. That's all I had for today, so I really appreciate everybody taking an hour out of their day to listen, and hopefully we have some questions that I can help answer. And again, thanks so much again to our CoCoRaHS staff for putting this webinar together.
Bill, this is Henry. Thank you for that very concise and interesting presentation. We really appreciate you taking the time today to be with us. We've got a little long, but we're going to stay on for about 15 minutes to answer some questions. And again, if your question is not answered on the air today, we will, Bill will try to follow up with folks. We're getting a bunch of them coming in right now, so we will follow up with that. Let's go to our questions. Right. Go ahead.
Yeah, I was going to say thanks, and I assume you'll just let me know of the questions.
Yep. Okay. Here we go. Mike in Ohio asks, how does CoCoRaHS daily accumulations assist in the hourly temporal analysis?
Well, the CoCoRaHS daily rainfall amounts are looked at on a daily basis, and so what we do is we take in that data for a given storm analysis domain of all the CoCoRaHS observations that have come in for that day, and then we compare that to the SPA storm analysis that's been completed for that location up to that given time as a QCing mechanism. So in other words, that CoCoRaHS data, an observer may have said 10 inches fell at their house, but our initial SPAS analysis maybe says it was only 9 inches or 11 inches, or maybe it says 18 inches. And so we do a comparison to QC against that, and we use all the given CoCoRaHS observations in that area as a way to QC what we're looking at from the automated sources and from the weather radar. That's in the real-time analysis. On a post-storm analysis, kind of the ones that we looked at in this presentation, that CoCoRaHS data is taken as a daily report and then is disaggregated into an hourly time series, basically. And that's done by using other nearby hourly stations to time that CoCoRaHS report and kind of break it down into what would have been hourly increments had that daily observation been an hourly observation. And that's very important information. And then one step further, if that CoCoRaHS observer had included notes about timing, I had 4 inches of rain in 2.5 hours between 5 and 7:30 p.m., and then another inch of rain between midnight and 1 a.m., that data is used as well to help disaggregate that daily report. And so it's initially started as a daily information, and then it gets disaggregated down into an hourly time increment based on nearby information.
Okay, Bill, thanks. Here's another one from Diane in Minnesota. She wants to know, how will your analysis strategies change with the Weather Service's transition to dual-pole radar?
Yeah, dual polarization is really going to help us out a lot. We're really looking forward to that. Of course, dual polarization radar is basically an advanced way to look at the raindrop size and distribution and rainfall accumulation within a given radar site's data set. And it's a huge advancement over what the current NEXRAD weather radar is able to do. And so what that's going to help us is it's going to help us to calibrate that ZR relationship even more efficiently and effectively. And really, it's going to take out a lot of the upfront work. The data we should be getting in native from the dual pole radars is probably going to be much better calibrated already. The magnitudes of that rainfall should already be much more accurate and realistic to what's actually happening. And so therefore, it should save us a lot of time and effort of SPAs having to go in and recalibrate and come up with that best fit ZR equation, because it should already be a much more accurate data set to begin with, and therefore require a lot less work, back-end work on our end. So we're really looking forward to that.
Kevin writes and said he was surprised to learn that the Nashville, Tennessee flood of 2010 was an AR atmospheric river-driven event. Any other storms east of the Divide come to mind being AR events?
Yeah, I mean, that's one of the neat things about the research that they found out, was that Nashville 2010 event had such a deep connection to the atmospheric river. In this case, they call it the Mayan Express out there. And what we're finding out as we go back and look at storms and continue that research, what they're finding out is that in almost all cases of large rainfall events or large snowfall events, there's almost always a tap to that moisture from the equatorial regions. I mean, it's a very, very common case. It's more common in situations where the rainfall or storm event is of a longer duration, a larger area size. You know, the thunderstorm events that occur so often in the Midwest and Southeast and East Coast, those ones generally aren't tapping into that atmospheric river, but the larger big ones are. And like I mentioned, the other storm we looked at, Snowmageddon, the mega snowstorm on the East Coast, they found out was tapping directly into that atmospheric river along the East Coast too. And so if you're curious to learn more about that, in my slide set, I had a link to the paper on that Nashville 2010 storm, which talks a lot about that. And if you just take some time to Google or Bing atmospheric rivers or Mayan Express, there's a couple of great sites which show a lot of the current research going on with that. And one of them is out of Boulder there, where Marty Ralph has a great site from the ESRL site, which does a lot on atmospheric rivers. So definitely take some more time to look into that if you want.
Okay, speaking of atmospheric rivers, Glenn writes and wants to know what happens when the west-to-east atmospheric river west-to-east atmospheric river encounters a hurricane coming from east to west.
Yeah, that's a great question. You know, I haven't seen any specific research yet on the connection of atmospheric rivers into a tropical system environment, but it seems intuitively obvious that the amount of moisture associated with some of those landfalling hurricanes or hurricanes would certainly be able to be enhanced a bit if you had an atmospheric river connection. The issue, though, just off the top of my head, is although you have these atmospheric rivers transporting huge amounts of moisture from the equator up towards the polar regions, that moisture still has to have some mechanism to turn it to rainfall on the ground. And so when you think about rainfall in the most basic form, to get rainfall on the ground, you have to have two things. You have to have moisture and you have to have lift. And so when you think about a hurricane or a tropical system, hurricanes are warm core systems. There are no fronts or fronts associated with hurricanes. They're simply a warm core system. And so you may not have the lifting mechanism inherent in a hurricane to turn that atmospheric river moisture into rainfall on the ground. Now, I don't know that that's for sure the case, but that might be a limiting mechanism. Now, once a hurricane makes landfall, oftentimes they will interact with a front, and at that point, you know, they become extratropical, and at that point, if you have an atmospheric river coming in at the same time, that certainly could enhance the moisture and add to the amount of rainfall on the ground. So that'd be a pretty cool area of research. Hopefully somebody's looking at that, because it might be interesting to take a look at how that interaction occurs.
Okay, Doug from New Hampshire writes, you showed atmospheric river data over the oceans. Is there interest in rainfall events over the ocean, even if the storm never makes a landfall, and why or why not?
Yeah, that's kind of like the old, if a bear does something in the woods or something like that, right? We won't quite go there, but yeah, that's the same kind of thing. Certainly those atmospheric rivers occur over the oceans, and it certainly rains very heavily over the oceans, just like it does on land. But again, as I just mentioned, you have to have some mechanism of lift to turn that moisture from the atmospheric river in the atmosphere to rainfall on the ground. And so as long as you have a front coming across the area where the atmospheric river is occurring over the ocean, you certainly can have the heavy rainfall associated with it. I mean, when we look at those atmospheric rivers along the west coast, it's not just raining on land. It certainly is raining heavily off the coast there as well. And so as long as you have a lifting mechanism, in this case it would have to be a front because you don't have any topography over the ocean, you don't have any mountains, it can certainly cause rainfall in those areas as well.
Patrice from Colorado Springs asks, are your precipitation studies added to larger climate data sets?
I hope so, but right now what happens is when we do these precipitation studies, they usually are done for a specific client, and they're used for that specific study. And then once it's done, you know, it kind of is housed by whoever had paid for that information. But one thing that is going on the government level, national level, is there's an extreme storms working group that's been formed to try to kind of regenerate, re-energize that system that was in place before and kind of set up a national cataloging system of big storm events. And so we are certainly trying to be involved in that and help them to set up that system, and then also to utilize the 200+ storms that we've already done, so they're not reinventing the wheel and wasting time and money analyzing storms that have already been done, but trying to work collaboratively with them on that system so we can have a nice catalog so that everybody that needs to use this data can have it available to them.
Okay, a lot of questions about atmospheric rivers. Here's one here from Chris. He wants to know, is there a correlation between El Nino, La Nina, and atmospheric river events?
Yeah, in all the research that I've read, I haven't seen a specific one-to-one correlation as far as more or less atmospheric rivers occurring because of El Nino or the ENSO cycle. But certainly what you have as a correlation with an atmospheric river and the ENSO cycle is where those atmospheric rivers affect certain areas and the strength of their effect. And so what that means is during an El Nino period, what happens is in the Pacific Northwest, as an example, you have generally less active storm track in the Pacific Northwest, less vigorous fronts coming through less often. And so if you may have the same amount of atmospheric rivers affecting the Olympic Peninsula of Washington State, let's say, but because you have a lower number of fronts coming through, some of those may not ever really turn into rainfall or very big rainfall. while the opposite happens in Southern California. If you have a strong El Nino, Southern California is almost always wetter than normal. Especially the dividing line, by the way, on the West Coast between wet and dry El Nino, La Nina, is about the 40-degree north latitude, right about Northern California. It's a pretty amazing line there where during an El Nino it's dry to the north, and during the La Nina it's wet to the north, and vice versa to the south. And so anyway, if you're in a La Nina pattern in the Pacific Northwest, you're going to have a more active storm track on average, more fronts coming through, more vigorous fronts, and so on. And so even if the atmospheric river events may be the same as any other given year, if you have more fronts coming through to potentially interact with those fronts, you're obviously going to have a better chance of getting more atmospheric river-forced rainfall events as well. So again, as far as the ENSO cycle goes, I'm not familiar with any conclusions yet on whether atmospheric rivers become more active or not, depending on ENSO cycle, but certainly the interactions and results of those atmospheric river events are going to be affected by whether it's an El Nino or La Nina year in a given location.
Henry, based on the interest today, we may want to do a Weather Talk webinar on atmospheric rivers next year.
Yeah, this is
and Nolan, I assume you guys are in contact with Marty Ralph down there in Boulder quite often.
Right, and one of our former CoCoRaHS leaders, Rob Cifelli, is a part of that group there.
Yeah, they do a lot of work on that, so that'd be very interesting.
Well, we're at the bottom of the hour. We're going to take one or two more questions, and then Bill can hopefully answer the rest offline. And again, most of them are on atmospheric rivers. It's pretty fascinating. Cindy from New York asked, can you explain how the Mayan atmospheric river relates to Gulf moisture in the east? Usually Gulf moisture is cited as a cause of precipitation.
Yeah, exactly right, and they are interrelated. Now, when we talk about Gulf moisture moving up the Midwest or the East Coast and feeding, say, the low-level jet or thunderstorms and so on, it's a little bit of a different delineation within the atmosphere that we're talking about. Generally, if you can picture what's going on there on around the East Coast, you have the Bermuda High, which is a semi-permanent area of high pressure that's positioned over the Atlantic Ocean off the East Coast. And again, the air flows clockwise around that high pressure, and so as it flows around that high pressure, it picks up moisture off the Gulf of Mexico and transports it into the eastern U.S. Well, when it's picking up that moisture, it's picking it up from surface evaporation off the Gulf of Mexico and from boundary layer moisture, in other words, say the lowest 1,000 feet of the atmosphere off the Gulf of Mexico and so on, and transporting it into the atmosphere over the continental U.S. east of the Rockies. When we talk about an atmospheric river, or in this case on the East Coast, it's known as the Mayan Express as well, we're talking about a deep layer of water vapor in the atmosphere extending really all the way from, say, 60,000 feet down to the surface. So the total column of the atmosphere that we're looking at. Now, an atmospheric river itself has a specific definition. It's kind of a narrow ribbon of moisture pretty much at about 2,000 to 7,000 feet above the surface, usually about 100 miles wide and maybe a 1,000 miles long. So it's a narrow ribbon of moisture that emanates again from the equator. So when generally when you hear on a newscast or a weather forecast somebody talking about Gulf moisture feeding a storm or Gulf moisture flowing into the East Coast or Midwest, they're talking about two different things. They generally are not talking about an atmospheric river. They're talking about simply moisture evaporating from the very warm waters of the Gulf of Mexico and affecting the atmosphere kind of right above its surface there and moving in and feeding the low levels of a storm, while the atmospheric river is a different phenomenon. And again, I think like Nolan and Henry said, if we had a whole webinar on atmospheric rivers, that could probably be made even clearer.
Okay, we're going to take two more. Actually, here's a suggestion from Diane in Minnesota. She's actually at the River Forecast Center there, and she was saying you might consider studying the Wisconsin-Minnesota flash flood September 22nd, 23rd, 2010. So this will be in the list of questions you'll get later, Bill, but just to pass that on to you. Okay, we're gonna take the last question, and Jim had asked. Well, actually, we're going to take two questions. Jimmy in Brownsville wants to know, is there a place online you can look up current information on atmospheric rivers? And if you have that, we'll put that on the website as well, if you can send me that.
Okay. Just real quick, there is a great site for that, and I will send you the link to it.
Okay.
And I'll give you the link, Henry, so you can put that online.
Yep.
By the way, that link is listed on one of the slides where I was showing the atmospheric rivers around the globe. There's a link on the bottom there to that site, and I will put that online as well.
Okay, and the last question of the day, Jim asks, with current climate warming, are atmospheric rivers increasing in intensity?
Yeah, so obviously climate change is a hot topic. The climate has always changed and will always continue to change, both warmer and colder. And certainly how a warming climate, if the climate was to warm, how that might affect atmospheric rivers is certainly a big area of research. And there, as far as I can tell, I haven't seen any conclusions on that, because what happens is when the climate warms, it's not a one-to-one relationship with all of a sudden, okay, we have more moisture in the atmosphere, we have warmer temperatures, and so because of that, this happens. Because what happens when the climate warms or cools, the storm dynamics and the way that the air masses interact and what's called the baroclinicity, or the thermal gradient between the air masses, is also adjusted. And so that also has a ripple effect. And that's one of the reasons that no matter which way you're looking at climate change, whether it's colder or warmer, we don't have a real good grasp of how that affects a lot of the different parameters in the atmosphere, because we still don't have a very good understanding of a lot of the interactions that occur in the atmosphere. That's kind of ongoing research that will continue to be refined as we continue to learn more about how meteorology and climate works, and how various parameters interact within the atmosphere, and how when one of those parameters changes, it changes some other parameter, both negative and positive feedback. I mean, there's so many myriad of things there that I'm not aware of any conclusions on how climate change, whether warm or cold, would affect atmospheric rivers, except to say that certainly storms become more vigorous, fronts become more common and more powerful when the climate cools, when there's a larger thermal gradient between the poles and the equator. While when the climate warms and there's less of a thermal gradient between the poles and the equator, you have less intense and less frequent frontal events. And remembering that atmospheric rivers need some kind of triggering mechanism to produce rainfall, and usually that triggering mechanism is a front. If you have less fronts and less vigorous fronts, you may be able to conclude that if the climate was warmer and there was less of a thermal gradient between the poles and the equator, maybe you wouldn't have as many heavy rainfalls as a result of atmospheric rivers. But then on the other side, maybe something else compensates for that. So that's a long way to say that I don't know, and the research is ongoing.
Well, Bill, thank you again for a very fascinating webinar today. We learned an awful lot. There's a lot for us to go back and think about. Nolan, any last words?
Well, the take-home message that I take from this is you never know when you're going to be in the bullseye of the next really, really monstrous storm. And it can happen anywhere in the country. And our gauges only hold a little over 11 inches. And some of these storms that Bill's been talking about here are distinctly more than that. So it's something we just need to think about. What would we do when the really, really big storm comes to our community, and will we be able to get the best quality observations that we can? So I appreciate everybody who came online to listen to the webinar today and to ask questions, and I bet you there will be a follow-up on atmospheric rivers based on this amazing response today.
Well, thank you, everyone out there, for being with us today. Please join us for our next Weather Talk webinar. It'll be next month on September 20th. You want to mark that on your calendars. It'll feature Dave Shagnon from Northern Illinois University, and he's going to talk about So You Want to Become a Meteorologist. It'll be great for students out there, or any of you guys who are interested in what it takes to become a meteorologist. So for Nolan and the rest of the gang here at the Climate Center, we thank you for joining us today, and we'll have this online shortly. Take care. Have a good day.